Okay, say we have this following electrochemical cell that we've studied before, the zinc copper 2+ cell, and we have our two beakers and our two half reactions separated, and we have electrodes connected by a wire, and electrons will flow through the wire. So if we want to write this electrochemical cell, this is a lot of writing. So we want to have a convenient shorthand way of writing the electrochemical cell. So what we do is we usually write the oxidation on the left side, and then we'll separate that of the reduction by two vertical lines. So we'll have the oxidation reaction written on the left, the reduction reaction written on the right, separated by two lines. So the two lines means the separation of the two beakers and the salt bridge. If we're going to write the oxidation, it's zinc going to zinc 2+. So this is the oxidation reaction. So that's the oxidation reaction. So we will write the oxidation, and on either side, oxidation or reduction, we're going to separate phases by a single vertical line. So we have zinc solid in an electrode and zinc 2+ in solution. So we'll separate those with a single vertical line. So this just means separate phases. And then we have our double vertical line, meaning this half reaction is separated from the copper half reaction. And in the copper half reaction, we'll write copper 2+ aqueous. We use a single vertical line to separate the copper 2+ in the aqueous phase from the copper in the solid phase. And so this is a shorthand way of writing this electrochemical cell. We write this in terms of the oxidation. So this is the reaction that's occurring, zinc to zinc 2+. And in the reduction reaction, we have copper 2+ gaining 2 electrons, going to copper solid. So we write these reactions in order of the oxidation and reduction. So in the oxidation, we have zinc solid going to zinc 2+. So we write zinc solid going to zinc 2+. In the reduction reaction, we have copper 2+ going to copper solid. So we start with copper 2+, end with copper solid, left to right. So this is a way, shorthand way, of writing our particular electrochemical cell. Now say we have like the standard hydrogen electrode, where we don't have an electrode, because here, if we had our standard hydrogen electrode, we would use platinum as the electrode. We would have H+ here, and we would have H2 gas above the solution. And so here we would write the oxidation is the same, but now on the right we have the standard hydrogen electrode. So we would have H+ aqueous phase, and we'd have H2 in the gas phase. So we have H+ going to H2 gas, and then we have another vertical line. So then we have a vertical line to separate the aqueous phase from the gas phase. Now we'll have another vertical line to separate it from the solid electrode. Now this just shows you what the solid electrode is. The electrode's not consumed in the reaction, unlike the zinc electrode. It's being consumed. Zinc's going to zinc 2+. So eventually this electrode will be consumed and the reaction will stop. But here, platinum is just serving as a surface for the reaction. So here, hydrogen can bump into the platinum electrode to gain the electrons. So the electrode in this case is just serving as a conduit for the electrons. It's not being consumed in the reaction. And so our half reaction for the standard hydrogen electrode is this half reaction. So now this half reaction is represented here, so we have H plus going to H2 gas, so I'll write H plus first, H2 gas second, and then it's happening on the platinum solid electrode. So this is the way we can abbreviate an electrochemical cell and reconstruct the cell from this abbreviation without having to draw an expansive picture. Now, one thing you'll notice is that I haven't balanced the equation. So we don't balance the equation here. We can balance the half reaction from this if necessary, but we don't write the balanced equation, and we don't write the number of electrons in this shorthand way. But once we get the half reactions and balance the reaction, we know how many electrons have been transferred.